Hey everyone, my name is Shreyas.
And my name is Shraman.
And we'll present our work on the development of an early warning system for foodborne illnesses using Google and Twitter search data. Foodborne illnesses are a major problem in the world, with 1 in 6 people suffering from foodborne illnesses. And this causes 420,000 deaths worldwide and 3,000 deaths in the United States. Further, foodborne illnesses cost the US economy close to $78 billion. To help prevent the spread of these outbreaks, local, state, national, and multinational organizations have created protocols that can dramatically slow down an outbreak. However, as you can see in the epicurve, the effectiveness of the protocols are directly dependent on how fast they can determine the existence of an outbreak, which in oftentimes is way too late, leading to massive losses. Thus, if the existence of the outbreak is determined early, then it can greatly decrease losses and help curb the speed of the outbreak dramatically. In this research, we propose a model for the early warning of foodborne outbreaks by analyzing internet search data, specifically Google and Twitter search data. We hypothesize that in a time of an outbreak, people affected by the outbreak will search terms related to the disease, which will cause a spike in those terms. Since it is likely that individuals who search these disease-related terms will do so before seeking medical attention, a model that can identify these spikes can identify outbreaks much quicker than existing systems. Thus, this research focuses on developing a mathematical and computational model to recognize these spikes in search data that corresponds to foodborne outbreaks.
First, we'll talk about the methodology that we use to create these models. In this research, we used 5 foodborne symptoms, which are not only common, but also pertain mostly to foodborne illnesses using data obtained from the CDC. After this analysis, we came to the conclusion that the following 5 symptoms were our best symptom search terms in our model. These were nausea, vomiting, stomach cramps, stomach flu, and diarrhea. We also incorporate the 5 most common foodborne illness terms itself as search terms in our model. Currently, these are norovirus, salmonella, Clostridium perfringens, Campylobacter, and Staphylococcus aureus. The Google search data is obtained from Google Trends, and the Twitter data is obtained from the Twitter streaming API. The outbreak data were obtained from CDC's National Outbreak Reporting System, NORS. As we have Google Trends and Twitter data only from 2013 to 2018, only these years are taken into consideration when developing our model. Before we start developing models, we'll have to pre-process data. In this research, we will use feature selection, feature optimization using principal components analysis, normalization, imputation, data shifting, and smoothing as data pre-processing techniques. We're interested in the difference between the search values. So instead of taking the absolute value of search terms inputs, we take into account the difference between search terms in consecutive days as inputs to our model. We take into account search data for the past 5 days for the use of the model. This gives us 4 differences, as you can see here. Thus, for each search term, we will have 4 additional features. And because we have 10 search terms, as mentioned earlier, 5 for symptoms and 5 for illness itself, we will have 4 times 10 equals 40 features. But we also incorporate data from Google and Twitter. So we have 40 times 2 equals 80 overall search features. Our model also employs population dynamics and historical foodborne illness features. And this is done because a particular locale can greatly influence the amount of cases. Specifically, our model takes into account the average number of foodborne illnesses per kilometer squared relative to the population. That is average cases per day per population density. We also take into account the average cases per day for the last 5 days. However, this approach will lead to over 80 features from search alone, as we said earlier, and even more from population dynamics. And this will cause the model to pick up on noise as opposed to the actual patterns of the dataset, and will make it very computationally expensive to train. To solve these problems, we use principal components analysis to determine the optimal amount of features to successfully predict the number of foodborne illness cases 4 days from when the model is used. In the first step of principal components analysis, we perform ZScore Standardization to transform the input dataset to one that has a mean value of 0 and a standard deviation of 1. This is done for 2 main reasons. Firstly, we don't want to penalize a particular value solely due to its magnitude. And secondly, it's because of the fact that principal components analysis is highly sensitive to variance input variables. Specifically, we use the following equation for the standardization. Here, Z sub I represents the ith standardized value in the data column, X sub I represents the original value of a column, mu represents the arithmetic mean of the column, and sigma represents the standard deviation of the column. Now we seek to understand the degree of correlation between the 90 input features. And the 90 input features consist of 80 search features and 10 dynamic features. And to actually understand the degree of correlation, we compute a 90 by 90 covariance matrix, with each feature computed against each other. The covariance between two variables, classically represented by the letter Q, is defined and computed according to the following equation. And at the end, we have a 90 by 90 matrix. Next, we calculate the eigenvalue of the covariance matrix to compute the principal components of the matrix. Principal components are linear combinations of these raw inputs, and those are made to be relatively independent. So each principal component is made to be relatively independent. As we have 90 input features, we will have 90 principal components. However, our model will not take into input all 90 principal components, as many of them have low predictive power and thus can lead our models to overfit. We will choose the minimum amount of features that explain at least 95% of the variance. And it was found that around 95% of the variance was explained by 10 features as shown in the graph. To overcome the problem of missing data, a process known as imputation was used. Specifically, the missing value is computed by running least square regressions on the missing data point a fixed amount of times and then averaging the results. This is done by using the following equation and then dividing this by the number n. To align our data set to our objective of predicting outbreaks 4 days before, we shift the date of cases in our data set by 4 days. We developed two models to predict the number of cases of foodborne illnesses 4 days into the future. One uses an artificial neural network and the other uses a generalized model. We first developed an artificial neural network to predict the expected number of foodborne illness cases depending on Google and Twitter search data, along with population dynamics data and frequency of foodborne illness in that area. An artificial neural network is an algorithm that takes in some input in the first layer, performs computations on the weighted inputs and applies activation functions in the hidden layer, and outputs the desired result in the output layer. In this case, the output will be the expected number of cases 4 days into the future. The connection between the nodes and hidden layers and things of that nature generate pattern recognition capabilities similar to those generated by neurons in synapses in the human brain. Hyperparameters, which are a term that refers to the parameters that affect the neural network training process itself, such as the number of nodes in each layer and the number of layers and things of that nature, are computed using a process known as random search. And random search consisted of performing experiments where the hyperparameter value was sampled using a normal distribution, and the choice that maximized accuracy on the cross-validation test was chosen. The following neural network architecture, consisting of 3 hidden layers with 4 nodes each, was found to be optimal after doing random search. An artificial neural network is trained by computing weights that minimize a given cost function. In this research, we used the log-loss cost function and the BFGS optimization algorithm to minimize the cost function. To train and test the models, we randomly stored the dataset consisting of the 10 principal components and the foodborne case data. And we use the first 60% for training. We use the next 20% for cross-validation to compute the hyperparameter values, and the rest 20% is used to test the model itself. The artificial neural network is developed using the Python programming language and TensorFlow machine learning library. And after running through 25 iterations, R-squared value of 0.97 was found. While a neural network is very powerful, one significant disadvantage with this approach is that a neural network is very hard to interpret. That is, if a stakeholder asks exactly what a neural network is doing to determine the number of cases 4 days in the future, then it would be very difficult for the neural net to do so. To that end, we also developed a generalized additive model, a model known for interpretability. A generalized additive model is an extension of classic statistical techniques such as polynomial regression, and that it's represented by a linear combination of terms. However, this model differs from traditional techniques because it does not restrict itself to a single family of functions. Specifically, a Gamm model is represented by the following equation, where b sub k of x is a term from some family of functions. The Gamm model was also tested on a disjoint 20% of the data. The family of functions used ranged from polynomial to Gaussian. The R-squared score for this model was 0.94. While the model did have a lower R-squared score than the artificial neural network, it was significantly easier to train and provides a direct interpretation of the model. Public health agencies should use a unanimous determination of both models to accurately predict outbreaks.
There are 3 distinct groups who are affected by foodborne illnesses.
The first group is the government agencies, in particular public health agencies. These agencies are responsible for the identification and mitigation of foodborne diseases. The second group is the people or the patients who suffer from foodborne illnesses, and the third group is the business that is responsible for the outbreak. Now we'll discuss in greater depth the specific risks associated with each subgroup. And we'll first talk about the US economy. A study by Scraff estimated that the total cost of foodborne illnesses to US residents is $77.7 billion. Further, according to the most recent accounts by the CDC, there are 47.8 million cases of foodborne illnesses in the United States. Thus, dividing these quantities, we can see that it costs an average resident $1,628. Now, let's talk about the businesses. So, foodborne outbreaks can cost restaurants and businesses in general greatly. Specifically, the two main costs to a business and to an extension and insurance provider are medical costs and legal costs. Firstly, according to a study by Michelle Shapiro, legal fees are very erratic, costing between $6,300 to $2.1 million. Further, there's only a weak positive correlation between the severity and amount of legal fees, according to an analysis by Barsh, the results of which is shown in this graph. On the contrary, revenue losses are proportionate with the size of an outbreak. This graph depicts the distribution of the outbreak cases, which are usually from 5 to 250, with an expected value of 74. However, it is important to note that there are many cases which are much greater than 250 cases, many nearing 1,000 cases, and these are not uncommon. For an affected individual, depending on the type of pathogen, it takes anywhere between 1 to 2 weeks to get cured. 0.26% get hospitalized, and out of them, 2.34% die. In terms of financial risk, the cost of treatment, loss of pay, or loss of a job are the major risks for the public and on an average, it costs $1,628 per incident. Our model could predict the risk 4 days before an outbreak happens, giving the public health agency the most valuable time in an outbreak to detect the cause and eliminate it. The most cases happen in the peak, and this model can successfully flatten the curve. With this simulation, this chart shows the number of cases with and without the model, red representing without the model and blue representing with the model. And it's a reduction of as much as 65% of the total number of cases because of those precious 4 days. As active contact tracing has significant costs, the resulting cost savings is as much as 27%. Public health agencies go through a 5-step process for any foodborne outbreak, and they are detecting a possible outbreak through public health surveillance, finding more cases in the outbreak, generating a hypothesis through interviews with sick people, testing the hypothesis to find a likely source, and if no source is found, you go back to step 3, which is generate. The final step is to solve sources of the outbreak and pinpoint the ultimate contamination. This model is recommended to be used at the first step of the public health surveillance system, that is the detect step. These two timelines are the depiction of an outbreak timeline with and without the model. With the model, the intervention or elimination of the cause can be achieved almost 8 days before. With the model, the number of cases are smaller. We recommend that insurance companies underwrite a policy where they may check if the public health agency in that area is using the model. If they do, the medical cost portion of the premium can come down or to provide an incentive, as medical costs are proportionally less with the less case count. The total premium will not be proportionally less as part of it goes for legal costs, and though the legal costs will be less with a smaller outbreak, legal costs don't come down proportionally with the case count. The model brings down the cost of an outbreak by 27%. With an estimated $77.7 billion annual cost of foodborne illnesses in the United States, the model will save an estimated $20.84 billion and potentially will save more than 1,900 American lives. We strongly recommend to use the model in surveillance of foodborne illnesses. Thank you.